Okay, so I'm Mark James. I'm a philosopher in cognitive science, and Tesh and I are both part of something called, that's my cat, forgive her. Tesh and I are some part of something called the Embodied Cognitive Science Unit. We're situated in the Okinawa Institute of Science and Technology in Japan, and our PI in the unit is Tom Froese. And the unit was kind of set up in the tradition of someone like Francisco Varela, intended to be a kind of scientific inquiry into a kind of generally non-representational approach to cognition. Um, maybe the kind of like maybe guiding motto of our unit is the idea that interaction matters. So that's interaction between, say, brain, body, and environment, but also individual person and the various scales that both comprise them and they help comprise. So we have projects on the individual sense of agency, on sensory substitution. We have some projects looking at dyadic interaction, be they, say, real-time reciprocal interaction face-to-face or in digitally mediated environments. We have people looking at collectives, so like criticality in swarms of bees or in teams. We also have archaeologists looking at the emergence of social complexity, and even astrobiologists looking at resilience at a planetary scale. And at least part of the ambition is to acknowledge the kind of synthesis across these scales and how all these things interact, which is an ongoing work, as you might imagine. Our unit PI himself tends to be focused on questions related to the interaction of, let's say, mind and matter, so questions around consciousness. Personally, I'm interested in how all these interactions can be leveraged in a kind of practical sense to serve the redirection of our behavior towards health, I guess, broadly speaking. And Tesh, I guess, is one of the people working on one of the models that we find helpful in all of this to think about how these systems learn and evolve together. So that's the notion of self-optimization. So I'm happy to jump back in for any sort of questions or whatever, but I'll let Tesh take it over from here.
Thank you, Mark. Yeah, so Tash or Natalia officially, just a bit about my background. I'm originally trained as a chemist, and I did theoretical chemistry for my master's. Then during my PhD in OIST, I found an opportunity to switch to the field of cognitive science, and I got very lucky in that I could combine the skills I had with a topic I find very interesting. So the work that I will present you today is based on this paper we published in December. In it, we show that how can we leverage the power of associative memory of Hopfield neural networks to solve complex logical problems, specifically propositional satisfiability problems. This paper is fairly technical, but it ties neatly with what I want to do in my own research project, which is related to creativity. Because with this computational model, we get to explore how dynamical system can break constraints of a problem that it is supposed to solve. And constraints are integral to creativity. So Michael, you're familiar with this model, but just to be in the interest of being self-contained, I will give introduction to Hopfield networks and then the satisfiability problems, and I'll show how we can cover maps with it. So Hopfield neural networks, named after John Hopfield, are a form of recurrent network, meaning that there are back and forth connections between all the nodes of the network. To describe the dynamics of the system, we can use a vector of states S, where each node can be described either as a discrete or has a discrete or continuous value. In this work, we use a bipolar value of -1 and 1. We update the system asynchronously, meaning that at each step of the simulation, only one node is randomly picked and updated. The output of that node is a function of a weighted sum of all the inputs from all the nodes in the network. In this specific work, we use a simple threshold function, step threshold function. So then with this state update, what will happen is that the network will start rearranging itself depending on the sign and the value of the weight Wij between any two nodes. So Si might switch sign, or Sj might switch sign. And these rearrangements of signs will result in a different state of the system. We can then evaluate the difference between these two states using so-called energy function described by this mathematical formula, which reflects the misalignment of stress within the state. The minus sign indicates that the energy decreases as network moves towards a stable state. So at some point when the energy do not change anymore, we know that the system reached a stable state or an attractor. So Hopfield neural networks are recurrent neural networks that converge to a stable state. This convergence to a stable state can be used in several ways. So first, we can find the solution to a complex combinatorial problem. For example, the traveling salesman problem. This is a problem that you given a certain list of cities, and you need to find the shortest route visiting all the cities exactly once and return to the starting point. So Hopfield and Tang showed that if the connections of the Hopfield neural network, the weight matrix W, correspond to the constraints of this problem, then the natural dynamics of the system is to converge to a stable state that will correspond to a locally optimal solution to that problem, meaning one of the possible routes. Now, another way we can use this convergence to a stable state of Hopfield networks is to recall patterns, for example. And this is what Hopfield did in his original work. He showed that we can take some patterns, for example, images, and use Hebbian learning to store them in the network's connections. This is a learning rule often summarized as cells that fire together, wire together. If the system then is introduced to a partial pattern, some corrupted image of the stored memory, it will act as an associative memory and converge to a state representing that stored memory. Now, what I mentioned briefly before is that the usual dynamics of a Hopfield network is to converge to a local minimum. This is often results in a suboptimal solution. In fact, in that traveling salesman problem paper, Hopfield and Tang mentioned that the system will only find the shortest path 50% of the time. This problem, however, can be resolved if we use the associative memory capability of Hopfield network. So, and this is what Richard Watson and his colleagues did. They showed that if we take some abstract combinatorial optimization problem constraints of that problem will be again represented in the weights, but we will also update the weights using Hebbian learning with certain learning rate alpha, meaning that we imprint on the weight matrix every state it visits, and we also reset the system to some random initial state every time it converges to local minimum. Then the system can reach a global minimum, which potentially means the best solution. So this model, which we address as the self-optimization model in our group, was shown to be general enough to model various complex adaptive systems, from gene regulation networks to selfish agents and socio-political networks, to just name a few. And if I'm not mistaken, in the recent paper with you, Michael, you are using a slight modification of this model to show transition in agency. However, all of this research focuses mainly on abstract problems. Now, abstract problems are very important for providing understanding of the general behavior of the process. But when the weight matrix doesn't represent a concrete set of constraints, it is hard to analyze what exactly learning does to the system. And this is what we wanted to investigate in this work. We showed that the model can also solve concrete problems as well, specifically the satisfiability problems or SAT problems. And by having concrete problems, we can then provide an insight to the relationship between learning and breaking of the problem constraints. So just before I jump to the results, I want to give a quick overview of satisfiability problems. So satisfiability problems, or SAT in short, are questions in logic where you need to determine if there is a way to assign truth values to a variable such that a certain propositional formula is true. This has immense applications, since many important real-world problems in different scientific fields can be expressed as max K SAT, which means maximum satisfiability problems with a maximum of K literals per clause, and I'll explain what that means in a bit. So anything from planning problems in engineering and verifying software in computer science to solving bioinformatic problems. To give you an example of a problem, of a SAT problem, let's look at the liar's problem. So imagine we have a room with 4 people, Alice, Bob, Cal, and Dan, and some of them or all of them can make statements. Here, Alice says Dan is a liar, Dan says Bob is a truth teller, Cal says Bob is a liar. And so our goal is, given those statements, to find out who is actually the truth teller, who is a liar. These facts can be represented by a vector of states S, with the fact that the ith person is a liar or truth teller represented by the state Si, where if Si equals 1, it denotes that the person I being a truth teller, and Si equals 0, it denotes that the person being a liar. So from this statement, using these representations, we can build logical relations. And then from these relations, we can get our propositional formula. And if somebody doesn't have a background in satisfiability, I recommend this link here below as an initial tutorial. I initially didn't have background in satisfiability, so this was very useful to me. But what we see here in this propositional formula, each term in the brackets is essentially a clause. There are 2 literals per clause, and they're separated by an operator. Here, the operator inside the first term is an or disjunction, and the operators connecting each term, each brackets, each clause are operators of and or conjunction. So this is a formula of 6 clauses, so a conjunction of disjunctions. And each term here has 2 literals in the clause, so this is a max 2 set problem, so only 2 literals per each clause. This will be relevant in a bit. This is why I'm kind of explaining it. So now that we have this propositional formula, the next thing that we would do, we'll put it inside of a set solver, and there is a plethora of set solvers out there. There's a competition on set solvers every year in a very interesting field. And what a set solver does, essentially, it outputs two possible outputs. So either this propositional formula is satisfiable, and then it will provide us with an assignment of the values that we're interested in. So in this case, Alice and Cal are liars, Bob and Dan are truth tellers. Or it will output, no, it's unsatisfiable. So given those relations that we give it, we cannot satisfy this propositional formula. So in this work, what we were interested in is, can we take this propositional formula and instead using this SO model, such that if there is a solution, so the system will converge to a stable state with energy equals 0, and each node will represent our assignment. Or if there is no solution, or then the state will be with higher energy, such that every unit of an energy will represent how many clauses were not satisfied. So what we needed is a way of mapping this set problem to the Hopfield neural network. Fortunately, this mapping was already performed in the 90s, first by Gadi Pinkins and then followed by Juan Abdullah, and his method is the one we implement here. In short, given the description of the problem by the propositional formula, this method allows us to describe the formula as an energy expression. So then we can compare this expression term by term with the expression of the energy of the Hopfield network, and this will give us a weight matrix that will describe the set problem. So for this specific problem, a max 2 solve problem, as I said, the liar's problem. So similarly to when the weights describe the constraints of a traveling salesman problem, the dynamics of the system would give us the solution, the shortest path. By using this method, we can use any set problem, and the dynamics of the system will give us the solution to that set problem. So this is what we did. So using this model, we can look again at the liar's problem. We took a bit more, 50 people with 34 statements. So person 1 says person 44 is a liar, and so on. So what we see here in this plot A is how this weight matrix initially looks like, that represents those 34 statements. Then in this plot, what we see is basically the solutions. There's essentially 3 distribution of energies. First, let's look from 0 to 1000, the dark blue. This is basically regular Hopfield dynamics, no learning. What would happen if we just run the simulation for this weight matrix on the Hopfield dynamics and let it converge and then reset it again. So what we see is that there is basically the system explores all possible solutions. Sometimes it finds a correct solution. Sometimes it converges to a stable state of energy 4, meaning there's 4 clauses that were not satisfied. Now, the red part, the star 1000, is basically when we turn on the learning. This is the SO model. So what you see here is that after a certain amount of resets, the entire system converges to a global solution, the correct one, with energy equals 0, meaning it managed to find a state that satisfies all the constraints. And what is interesting is that once we turn off the learning, this is the light blue line at the end, even though we continue resetting the system to some random initial states, it stays on the global solution. So yeah, and just to show you, this is how the weight matrix looks like at the end of the simulation. So this is a system that augments its behavior with associative memory of its own attractors and self, and finds a global solution, hence optimization. Now, this is a simple example we use to show that indeed the SO model can solve sad problems, and that the learning improves the chance for arriving at a global solution. However, a more interesting scenario to examine is what happens when there is no solution to the problem. So for this, we use the map covering problem. So here we have the map of South America, and the goal is to cover all regions by distinct covers such that no two bordering regions have the same cover. So we only want to cover this with 2 covers. So this is not solvable problem. That's what I meant by that. You need 4 covers for this specific map. But we find this example interesting, and I'll explain why. So first of all, we represent the state of the map by matrix. Now here S is a matrix where Sij equals 1 denotes that region I has color J. This is a bit more complex notation, but it allows us to generalize the problem to the cases when we want to use more than 2 colors. So this is why we chose to use this notation. And this problem can be represented by these 3 requirements. So each region must be covered. A region cannot be 2 distinct colors at the same time, because with this notation, computationally, numerically, we can have a solution. We can have a state like that, where the same region has different colors, and it doesn't make sense, but it can be allowed computationally. But this is a requirement that we need to have. So it cannot be 2 distinct colors. And the third requirement, regions that share a border should have a different color. So this is how we represent it logic-wise. You don't need to remember it. I'm just showing it. It's a bit more complex than the liar's problem. And so these are 3 different sets of constraints, and our propositional formula would be basically a conjunction of those 3 sets. And here what we did, we also added weights to the sets of clauses, so to these constraints, so kind of our preferences, and I'll explain what it means. So if we don't add any weights, that's just taking these 3 sets of constraints. They all have the same weight. What you see here is how that weight matrix of map covering problem of South America would look like. But again, as I explained, we might have a situation where a certain region doesn't have a proper cover. So in order to avoid it, we also tried to put more weight on the first 2 sets of constraints, meaning that each region, first and foremost, must be a proper cover. Another way we also try to do this is, instead of putting more weights on the first set constraints, we thought, okay, we can adjust the weight on the third set of constraints by the border length of a country, meaning that adjacent regions are, the border between 2 countries. So meaning that adjacent regions are less forced to be covered differently if they have a shorter border. So if we look, for example, again on the map, if we look at Peru and Chile, we see that they share a very short border between them. So if they're covered the same color, it's not that bad. However, if we cover Chile and Argentina in the same color, since they share such a long border between them, that would be a bit more problematic. So this is what this third set of weights means. So here are the results. So here again, plot A and plot B show how the weight matrix representing the problem looks before and after the simulation. And then D basically shows the final product of the simulation, the converged state. And so here, dark blue and light blue basically are proper colors, and orange is non-color. So I know it's a bit hard to visualize what is non-color. So this is how we visualized it. So we see that there are 3 regions that are not a proper color, and the energy for that is E3. So that's correlates. So there's 3 clauses that were not satisfied. However, in this situation, there's no there's no point talking about borders between countries, because when you have non-cover, so this is basically why we did this additional weights. So in the second scenario, where we put weights now on making sure that all the regions have proper cover, now everything covered properly as anticipated. However, what we can see here is that, and maybe it's hard to see, but if you squeeze your eyes, there are 8 borders that were violated between the different regions, and the corresponding energy is 8. And the third one, with the borders one that we tried out, it's even worse energy-wise, but we can do that. We wanted to try it out and see what it gets us. So just to kind of have a short summary right now. So far, I was discussing the results from a satisfiability angle. We saw that the SO model can solve sad problems, and we examined how we can manipulate our preferences toward different solutions when we have this scenario where there is no correct solution. What I would like to do now is to switch to talk about particularly interesting result, and that is what we see here in last plot in the corner. So if we zoom on it, we can see the region of Costa Rica in the specific run has the same cover as Panama. Now, since nothing is attached to Costa Rica in this map, in principle, it should not cost anything to the system to flip the cover of Costa Rica to be distinct from the one Panama has. However, this is not the case. So what this example shows is how Hebbian learning can dramatically modify the weight matrix that encodes the problem of the constraints, such that some of these constraints are no longer contained within it. So in this example, in the unmodified weight matrix, the cover of Costa Rica can be trivially changed to satisfy the constraint on having opposite covers across borders. However, a state with that cover flipped is no longer in an energetic minimum of the learned weight matrix. And this is, we find it interesting because this would never happen in the traditional set solver. Of course, this is not a good solution, but this is obvious since this problem has no solution. This is even a worse solution, but that's not the point. The point is to try to investigate how breaking of constraints happens through learning. And that is hard to do in abstract problem because you can't understand what is a particular state means in relation to the original weight matrix. And with concrete problems like this, we can explore domains that were previously inaccessible. So the next step would be to try to basically investigate different problems and see how we can use this knowledge to explore different types of domains. So to just summarize again, so some limitations in future work, the SO model is much slower than the state-of-the-art SAT solver. But yeah, we were not trying to beat the SAT solvers. As the SO model has some potential for parallelization and it can be tweaked to work faster, but we find that it might be interesting for engineers that are interested in biological possibility, let's say, since it is much more biologically realistic than a SAT solver. Another thing with it is that, as I showed, the SO model, we did a max to SAT problems, and the SO model solves, cannot handle SAT, in principle, cannot handle SAT instances with more than 2 liters per clause. That's what you would think. However, we know that any K-SAT problem can be reduced to free SAT problem, and any free SAT problem can be reduced to max 2 SAT problem, in both cases at the expense of linear number of new variables. So this means that in principle, any K-SAT problem can be reduced to max 2 SAT problem, and then the SO model can be used to solve it. So it will have just much more, let's say, hidden variables. So about future work, so with this specific topic, now that we know that we have this kind of a connections between initial constraints and what happens to them after learning, we can ask, what did the system learn? And maybe, for example, if we look at the learned weight matrix, can we convert back to the logic and see what clauses were eliminated, for example? That's one idea for how the future work can go. So finally, I would like to acknowledge my co-authors, Werner Koch and Ozan Erdem, of course, Tom, and this is our lovely unit, and thank you for listening.
Well, thanks so much. That's super interesting. I have a couple of thoughts, and I don't, maybe this is obvious and you guys have already thought about it, but I'm just cluing into this now. So the first thing is, what occurs to me is that the initial set of requirements, the logical statements that you're modeling, you could think of it as a set of beliefs or preferences by an active agent of some sort. And what then you're doing is you're producing a network that can act as a controller for that agent that would navigate some space in a way that's consistent with its beliefs or preferences, right? So it's like, I think this is I hadn't thought about this before, but I think it's a very interesting map, because you're starting, and I can tell you some related things that we're doing to this, but it's like you're moving from a statement of what the system either believes to be true or would like to be true, and now you've got an actual biorealistic controller that seeks to implement it to you. So by satisfying it, what you're really doing is navigating a space to a region where the things that the agent is looking for are in fact true. Does that make sense to you, or have I misunderstood? I mean, it seems like this is an agent navigation task here.
Well, I love the way you think about it as an agent navigation task. It's so, so far my angle on this was always more technical. So I kind of always look for, well, what is this agent in kind of represent? But then I would love to try it out. But then how would you describe the problem, let's say?
Well, the problem is when I say agent, this could be a cell or an autonomous vehicle or whatever it's going to be. I am in a world, and I have, this is something Mark Solms talks about a lot, is this idea of having multiple constraints or multiple drives or needs, and your goal is to have all of them met, and sometimes it's impossible to have them all met. But so my drive is that I want in your initial case, this one is a liar, that one's not a liar. So I want this one. I want to be in a region of my space where this thing is true, and this thing is also true, and this other thing is not true. I want to not be hungry. I want to reproduce, and I want to be out of the danger zone in my environment. Right. So those are three things you want, and there are many areas where you can have one of the three, but not the other two, or two of the three. And maybe if you're lucky, there's a region of the space where all of those three things can be met, and that's where you would like to go. So this sounds to me like a typical problem of drive satisfaction for an agent that has a multi-dimensional set of things that it wants to maximize or optimize, and what you're looking at here, and so now, okay, so that's the thing you want. Now the question is, how do you get there? So you've got this landscape. How do you find the place that's going to meet all your requirements? And it sounds like you've got a mechanism here, which is actually a biorealistic controller of how you navigate that landscape. So what I love about this is that one way to think about the spectrum of agency is to really think about what the world looks like from the perspective of that agent, right? Like if you're dealing with a bowling ball on a landscape, all you need to know is your vision as a third-party observer, as your vision of the landscape. And that tells you the whole story of what's going to happen. But if you've got a mouse on the landscape, your view of the landscape doesn't matter that much. What you want to know the mouse's internal representation of that landscape. Where has he been rewarded, punished, what are the valences, right? Because you're not going to be able to predict his motion from your view of the landscape. You need to know what his view is. So what I see here is a really interesting formalism for specifying what are the drives and the goals and the preferences of an organism, and then you're basically producing a vision of the internal map of that organism of where, how does it feel about that space, and where are the places where it's going to be happiest, and where it's going to be happiest is where all the constraints are met, but at least having some of them met is better than none, right? So that's super cool, and now you've shown a map of the landscape, and you've the internal, kind of a first person perspective, the agent's view of the landscape, and an actual controller, an actionable biorealistic controller that it can use to get where it needs to go. I mean, I think that's amazing, and I think that's there's so many applications of this. Like, that's super cool.
Awesome. Yeah, sounds cool. Thank you. Yeah, I like the way the vision of internal map, I guess. I mean, it's I think the speculating a little about what would be the internal map of mice is a bit too much, I guess. But for us trying to, let's say, my goal initially was to understand, well, what you can manipulate, let's say, in the environment, such that you can satisfy, let's say, other different constraints. So and then you can see how that can help. Again, the actual map maybe doesn't even matter. What it matters is like we have this controller that we can modify.
Yeah, I mean, forget the mouse, but I think easily you could produce a minimal, a minimal agent in a virtual world that has some needs that it would like, some variables that it would like to be in a certain level, right? So you can either go with a true false thing, or you could do fuzzy logic and say, I want my hunger level maximized, but this other thing, I want my temperature in between this and this. So you have some statements of things you prefer. And literally use that Hopfield network as a controller and watch the agent navigate. I mean, you can actually watch it navigate its world. I think this is incredibly powerful for linking, because what you started with is a kind of not verbal is not right, but like an explicit description of what the agent might prefer. And from that, you got to a dynamical actual controller that might implement it. And that's really, I mean, I can think of all sorts of model systems where that would be useful. I'm also thinking in reverse. The thing you said at the end about trying to read the map at the end, right? So that sounds to me like a neural decoding task, where the idea is that so neuroscientists, what they want to do, they want to scan the brain, and from that they want to recover the propositional information that's there. So they want to read a bunch of electrophysiological signals and say, you remember having breakfast like this, and you believe in this, and you've never seen this, and this is your preference is that. So right, they want to recover those things. So this also, and we do this all the time, but we do it in outside the brain. So we will look at an early embryonic tissue, and we will say, okay, what shape do you believe you need to be? Because those are the kinds of things, like literally when we recover these bioelectrical pre-patterns, we can actually recover goal states, anatomical goal states. And to us, this is, again, just a navigation of anatomical state space, where we say, okay, I see where you're trying to get to is this particular region where you've got 5 fingers and you've got this size and whatever. So, so we try to do that decoding too, like look at the bioelectrics and say, okay, so what do you think you are? Are you a zebrafish? Are you a frog tail? What are you? And I really like this example too, your model, because that's like a simplified model where you can practice that, and you can say, could we look at the controller and the time, the time profile of the controller, and extract from that the logical statements, basically read the mind of the creature. What do you want to be true? What are your goals? Right?
We cannot do that yet, but I mean, I think maybe it's possible. And
yeah. No, I understand. I mean, we certainly, like, it's certainly in the neural context, it's also extremely hard. But this is a simplified version where we can maybe test some techniques, because there are some AI tools that are coming online for inverting some of these things. I mean, it's an inverse problem, right? This is what you're trying. Right. This is what you're trying to do. I think that's incredibly interesting. Do you know? And so just a related thing that might be interesting to you. Do you know the work of Patrick Grimm on the dynamical systems view of logical statements?
No, I do not, and I would be happy if you can forward me a paper too.
I'll send you. Yeah, he has it's very interesting, and it has a number of papers. So basically, just kind of briefly, it goes like this. So Grimm is a philosopher in New York, and in the 90s he developed the following thing. Consider the simple liar paradox. Okay, so you've got a sentence that says this sentence is false. The reason it's a paradox is that if you insist on a single unchanging truth value, then you're stuck, right? Because that doesn't work. However, Grimm did 2 things. One is he allowed it to have time, which means that what you can actually do is just view it as an oscillator. because as you go through the sentence, right, it's true, but then it's false, right? So you got the simple oscillator that just goes up and down. And so he gave it time, and then which immediately removes the paradoxical nature of it, because now there's no problem. It becomes a dynamical system. And then the next thing he did was to just go to fuzzy logic and say that, okay, sentences could have any value from 0 to 1. And now you can have groups of sentences that go like this. Sentence A might say, I am 80% as true as sentence B is false. And sentence B might say, I am 30% true. Okay, there's two sentences in there, and they refer to each other. And so now what you can do, now that you view them as dynamical systems, you can plot them. And you can either plot them as a function of time, and you get some sort of time-dependent behavior, or you can use the extra dimension and just make a static shape out of it. And so now what happens, right? And so they become, depending on your sentences, they become some of them are fractal, some of them are have weird attractors that are, some of them stabilize, right? Some groups of sentences stabilize, some don't, and some have all kinds of attractors and so on. So what it does is it again, which is what I saw here, a very cool connection between logical statements and sort of propositional content and dynamical behavior. And getting behavior out of logic, getting spatial, and again, spatial, I mean, the grim thing too is a kind of spatial navigation in some sort of truth space or something. I think is extremely interesting. So we're doing a bunch of work on that now, looking at the different types of sentences, right? So the liar paradox is a basic oscillator. All it does is, sort of, other things are even more boring. As a simple statement that has one truth value, just like sits there. This thing oscillates. Other systems have all kinds of complex behaviors. And once it becomes a dynamical system, then you can try to do something really crazy. And this is, I don't have any results on this yet, but just, as we've shown with models, dynamical systems models of gene regulatory networks, they're often trainable. In other words, they have 6 different kinds of memory that they can form from inputs. And so including Pavlovian conditioning, you can literally train these things. And so, and biological networks are much more trainable than random networks. So I think evolution actually likes that property. So now you can think about doing something completely nuts, which is to train to train groups of logical sentences. And right, and so if that's true, I think what happens is that you're not really training the sentences, you're training a virtual, an extremely simple virtual mind that contains those sentences as its cognitive commitments. That's what you're training, even though you're sort of neglecting the rest of it. We're not modeling the rest of the organism, we're just modeling that. So I think I need to think about this more, but I think that's one of the things that you have here is an amazing connection between the propositional content of an agent's mind and a behavior, a dynamical system controller that guides its behavior in space. I think that's pretty wild.
I like the way you phrase it. Maybe that will be the next paper.
Pretty wild. Yeah.
Yeah, I don't have a lot to add what you said. I mean, that's very nice thinking about it on a more kind of a meta level. Yeah, I would love to think about, if you're interested, we can maybe do it together, the next problem that the agent would be solving, and then try to implement in this model. I would be happy to do it. Yeah.
Absolutely, yeah, that'd be great. Yeah, no, I'd love to collaborate on that. Yeah, we have a number of virtual, simple virtual systems that we use them for making hybrids, where we have neurons. I mean, yeah. So one of the things that we have is living cells that are instrumentized to inhabit a virtual world. So by the signals they put out, that moves them around in a virtual environment, and then they get rewards and punishments for, they basically, it's basically a brain in a vat living in this virtual environment. And one thing we can do is, if we work a little bit on that inverse problem that we talked about, maybe we could actually apply it and pull out the cognitive commitments of that organism. So like, imagine you have a set of cells. They learn to navigate an environment where certain regions are good or bad, And then we use the reverse of the technique you just showed to extract a set of sentences where the thing literally tells you, I hate this region over here. I like this region here. And this is the region where all my needs are met. This is the region I like. We might be able to actually extract that, those statements in a very simplified, a three, just a couple dimensions, 3 dimensions or something.
Yeah, I think I understand what you would like to do. I mean, right now I feel, if you look at the weight matrices at the end, they're very simple. They're like rank 1 basically. So lots of information is gone. So I wonder how would that need to be modified to, let's say, if you want to remember more than one statement or more than things like that, then maybe it needs to get a bit more complex. But yeah.
Yeah. Well, and there's also, the issue of course, there's going to be more than one. Is that true? I think that's true. There's going to be more than one set of statements that are consistent with any given matrix. So we're not recovering one unique, mental snapshot that belongs to each of these things. This guy maybe the simplest one, which is okay, right? That's, kind of when we do theory of mind and agent-agent interaction. Again, we never know exactly what anybody's thinking, but you sort of say, what's the simplest model of my conversation partner that explains what's going on here? So I think that's fine. I think that's perfectly reasonable. Yeah, that's interesting. Okay, cool. So yeah, let me think about this some more and and come out. Yeah, this is great. And I'll come up with a couple of simple scenarios for things we can actually model, simple things we can actually model in this way.
Sounds fantastic. Thank you. Yeah.
Awesome.
Thank you so much.
Yeah. Any other thoughts from anybody? Werner, Mark, anything you guys want to add?
Just reflecting on what you're saying. I mean, it's something we're kind of looking at in a different domain, let's say at the moment, from a kind of behavioral design perspective, and trying to say, well, propositional content is maybe one dimension, but you also have, say, the kind of motivations and the sets of capacities and skills from a kind of more embodied perspective, and then the affordances of the environment. So, I mean, ultimately, if we can get to the point where we're kind of modeling the interaction between all of those elements, that would be fantastic, right? But something more simple is probably a good idea.
Yeah. And so one way to add that. So I've been thinking about this for our case, because if you have a group of sentences that refer to each other, right, in the kind of grim diagrams that I was talking about, I mean, that's all well and good, and you get a shape, but if they only refer to each other, they're not tethered to any kind of real world, right? They're sort of self-contained. They only refer to each other. But you can imagine having atoms in there that do refer to a real world or at least a virtual world for their embodiment. And you can say, sentence A could be, I am 50% as true as sentence B times however true sensor 1 is, right? And sensor 1 is some aspect of it's reading some aspect of the outside world. And so now that system is not just a self-contained logical system that sort of cycles in and of itself, but it's actually linked to the outside world, right? And you can even then you can imagine multiple agent interactions where here's a group of sentences A through C, and here's one, C through F. And they have C in common, which means there's a kind of chemistry that can be made when they come together. They have something in common, and they might end up being incompatible, or they might be compatible that knocks them into a particular region of the space. So you can imagine multi-agent interactions, and you can absolutely tether them to the real world by including variables in your sentences that correspond to some kind of affordance in the real world. Yeah. So I think you could.
So something else that seems to be interesting there, like what you're describing really does map to the kind of phenomenology of, let's say, the development of behavior, right? We have a bunch of commitments, and then we're trying to work out where the kind of congruence is between them. But actually, often, like, we fail to do that, right? As human beings, we kind of get stuck at times, and we say, I don't know where the kind of congruence is here, and that leads to ambivalence, and it leads to ultimately at times to disorder, right? So maybe there's actually the possibility in here to start like, okay, well, I have all these sets of things, and there is some tension, and maybe it seems incompatible. Can we have a model that helps us understand how you kind of resolve those tensions eventually? Maybe.
I have maybe one comment on what you said earlier about an agent and trying to satisfy the desires or needs or whatever. If you model that, I think a critical problem is how you weigh the different desires. Like if they all have the same weight and it's set up such that you cannot satisfy all constraints simultaneously, what sort of weights do you put in? Or ideally, you would want a system to have a way to determine that itself, because in the map coloring problem, it's very difficult to have the different sets of constraints. You cannot use the same weights, because then it will, in a problem where no solution exists, it will most likely find a solution that doesn't even have proper colors, which is why you should have weights attached to that in one form or another. But it's not obvious how you would let the system decide that itself. And I think if you have an agent with their desires trying to be met, you run into the same problem. How do you decide that? If you had some physical model that would lead to weights automatically, then okay, that's an option. But if it's just the system in an abstract space, then I don't think it's immediately obvious how you would do that. Mm. But ideally, you would have the system self-adjusting.
No, it's a great question, and I think I'm gonna show this to Mark Solms, because he's been thinking about these things a lot. He builds minimal agents with drives, with orthogonal drives. I think one way to do it would be to introduce a time aspect. So you're an agent and you have a bunch of drives, and the first thing that's going to kick in is thirst. And that kicks in before hunger, and you're not really going to be worried about hunger if you're really thirsty. But at some point, they both become sort of critical, right? So some things have a, you can almost imagine. I mean, this is like me imagining is on the fly, so maybe nonsense. But there's almost like a gradient sharpness, like a slope, where certain desires ramp up very quickly and others ramp up slowly, and so these weights might change. In a real organism, that's probably set to some extent anyway by evolution or by prior experience. Here, you could let it have control over those weights. So, for example, some of the values of your nodes in your network could actually feed back to tweak some of the weights, right? So, I mean, I can't even imagine what would happen if you did that, but that's easy enough to check. And it's also
that sounds like something that would easily become unstable. Like, I mean, the Hopfield network is it's stable, right? Like it converges to some state. But if you have feedback from the state into the weight matrix directly, I mean, the Hebbian learning does that to a certain extent, right? That is feedback, but it's stable if the learning rate is low enough.
Yeah.
If you start introducing direct feedback from the state into the weights, then I can see this spiraling out of control very quickly. And then you have the same problem on a meta level, that you as the experimenter need to twist knobs on the algorithm to keep stability.
Maybe you as the algorithm, or maybe we have a second network, like a metacognitive component, right? I could imagine ways to play with it. It may even be a model of psychological, the kind of thing where you have some incompatible drives that can't all be true at once, and then eventually you just decide that, what, this one thing, it's not worth it, it's killing all the other stuff, right? It's like yes, I really like that chocolate cake in the middle of the night, but it's just it's messing up my other stuff, and so I'm just gonna decide that's it, that one's out now. And so some ability to adding that metacognitive loop where there's some ability to re-weight them based on how things are going. If your experience is that, I could make 9 out of 10 happen, it's just that 10th one that just always, like, I'm not paying attention to that anymore. So you could imagine, and in biology, some of that works. I mean, you're never gonna be able to cross off with things like thirst and so on off your list, but other things you can, if it's really, and I bet there's I bet there are experimental data with probably rats or something, where after a while they just decide that within this environment there's one thing that they need to give up, and then life gets better. So I don't know. It seems like we could try various on top of the system you showed today, various kinds of changes that'll make that fly.
Yeah, that's a very simple model. So there's, I think there's many ways you can make it more complex and break our head of trying to make it stable.
Yeah, cool. Okay, well, fabulous. Thank you so much. That was really
Thank you,
interesting.
Michael.
Yeah, let me
Thank
ponder
you
it
so
some
much.
more, and we'll be in touch. I would be really interested in working together on this. No, it's great.
Great. Thank you so much. It was nice talking to you.